Hi everybody, thank you for the introduction. I also want to thank the neaSPAC organizer for this opportunity which is given even to newcomers like me in the field of SNOM to participate to such a very interesting workshop. Actually, I've learned so many things for the last 2 days, I'm really delighted. Well, as a beginner, I will spend most of my presentation to talk about non-near-field measurements, but you will obviously see why we wanted to jump into this very fascinating world of near-field imaging. And anyway, at the end of my talk, I will modestly show our first steps with the neaSNOM, even though we are at the very beginning of our journey with this technique. So, well, in this study, we are interested in antiferromagnets and multiferroics. And these are basically the two keywords of this title. And I also want to mention that this is a collaboration with our friends and colleagues from the CNRS lab. Can I do that too? Oh yes, it works, perfect. So antiferromagnetism is a peculiar kind of magnetic order where all spins are antiparallelly aligned. And as a first consequence of this is that there is no net magnetization inside the material, no fringing magnetic field, and that makes them very robust to external perturbations such as external magnetic field, but also very silent. And, but this is not the property which interests us the most. Actually, the most interesting property for us lies in their dynamical properties because their intrinsic resonance, intrinsic dynamics lies directly into the Terahertz range as nicely illustrated by this work where they could measure the 1 Terahertz antiferromagnetic resonance in the prototypical nickel oxide crystals. In other words, that means that these antiferromagnetic textures, they can be typically shuffled around, moved around on the picosecond time scales. That means that this is 3 orders of magnitude faster than their ferromagnetic counterparts, where all spins lies in the same direction, typically. But that brings us to basically one question: is what role could be played by antiferromagnets in future Terahertz and ultrafast devices, for example, especially if you consider the role played by the ferromagnetic-based spintronics in devices such as hard drive disk or new kind of memories. But for this, there are a couple of changes to be tackled, and in particular 2 of them. And this is by nature because of the antiferromagnetic textures, is that they are quite difficult to manipulate and to control, and for the very same reason, they are very difficult to observe, to image, and not only their static textures, but also their dynamic modes, for example, their excitation. But there is a trick we can use, especially, and this brings me to my second keyword, typically, especially if we're considering multiferroic materials. So multiferroic materials, these are this kind of materials which can host different ferroic orders. For example, ferroelectricity and magnetism. And most of the time, they are coupled together. That means that in the case of an antiferromagnetic materials and ferroelectric materials all together, we can think of using an electric field or the ferroelectric order to control the antiferromagnetic order. So this is a good handle. And so for this, the material of choice and the material we have chosen is the bismuth ferrite. And especially because it is both ferroelectric and antiferromagnetic, and with the 2 ordering temperature well above the room temperature. And you have to know that this is actually the only multiferroic which is both ferroelectric and antiferromagnetic at room temperature. So regarding the ferroelectric configuration, I have to mention it's a perovskite type of structures, but then the ferroelectric polarization can lie along one of each 1-1-1 direction in the pseudo-cubic lattice, okay? And for each of these polarization, then you can have 3 possible order for the spins, typically. And then, depending on the strain, either you can have this kind of fancy antiferrometric cycloid or a standard G-type antiferromagnet. But for the sample of today, it's thin epitaxial layers, 100 nanometers epitaxial layer grown by a pulse laser deposition system. And here you can see the piezo response force microscopy images where they basically image the ferroelectric configuration. So you can see typically as grown the typical size for this antiferrometric domain, which is in the range of 100 nanometers. And what I have to mention is that in this case, actually the animation, I should have killed this stuff, but then in this case we are in the G-type antiferromagnets. Okay, so we have the samples. So now we need to be able to image this kind of complex multiferroic order, and for this we do second harmonic generation. So this is the nonlinear optic technique. This is actually the lowest order of nonlinear optics, and I'm pretty sure you know, but I just remind you: is you shine a light at omega on the samples, and under certain conditions, typically symmetry breaking conditions, space and time, then the samples can generate light at twice the frequency, and if you collect it and analyze it, you can get a certain amount of information. So this is what we did, but obviously now you see why we need the near-field optics, because the first trick we used, we decided the samples are definitely too small, so we decided to write with the PFM tip, applying a voltage on the PFM tip, a large single ferroelectric domains. 10 by 10 microns, and we built a microscope, a transmission microscope, where it collects this light in a wide field manner, and these are the typical images you can get for different orientation of the polarization. What I have to mention is that our laser is a 1 kHz laser, 100 femtoseconds, and we have an OPA, and in this case the omega light, while the wavelength was 900 nanometers. But then for different orientation of the polarization, you can definitely see that you see the square, but for some other direction, then you see the substructures. And I will skip you all this symmetry analysis, but if you do pixel per pixel the angular dependence for the incoming polarization, then you can note that there is two kinds of families, basically. You do a bit of symmetry analysis, then you can separate one part, which is only the gray part related to the ferroelectric part, and then the color part, which is related basically to L. So in the single domain, it's basically L. And if you reconstruct this asymmetry, basically, you can have one image which gives you basically the antiferromatic ordering in a given ferroelectric patterns. So we could learn a couple of things. For example, the third domain is missing, etc., etc. I leave you with this paper if you're interested in. But then, as I said, we're also interested into the dynamics, so we can move to, let's say, a pump probe time resolve experiment. So now we have still a probe which is a second harmonic generation, and we pump with a large intense femtoseconds. Then basically we can take snapshots at different delay time, and then of our structures, and then we can do a bit more analysis, typically than looking at the asymmetry and a bit more stuff, but okay, I will skip this. But the asymmetry gives us the red and blue domain, especially well before the T0. And then once you have this antiferromatic pattern, then you can select blue and red domain and look at their intrinsic dynamics. And the idea we had here is basically, since it's a magnetoelectric, if we want to shuffle around the antiferromagnetism, we have to use ferroelectric polarization. And since it's a non-total symmetrical materials, if you shine an intense light of it, you generate a small dynamical polarization inside the material, which could be our ultrafast handle. So you can distinguish between red and blue domains and look at the time around T0, and what you have here, basically, you have some insight on this ultrafast polarization, so you can actually look at the full angular dependence to have a bit more information. And yes, and then if you look at longer times, then what you see in the two cases, you see the start of an oscillation and ultrafast decay here. And basically, I don't go into detail, but here the signature of what we call the electromagnons, basically, and it is known to be in the range of 800 or 700 to 800 nanometers to gigahertz for the bismuth ferrite. And here, since also we hit with an intense pulse, I forgot to mention it was 40 millijoules per square centimeters, and in 800 nanometers, we have actually the ultrafast antiferromatic demagnetization, typically. But the thing is now, is that, as you see, typically we are at the limit of what we can do with far-field optics. So this is, we need definitely a better spatial resolution. And then we got inspired by the work of Marcus Raschke, where they did this near-field imaging, second harmonic near-field imaging, on also a multiferroic material, and they could nicely image the antiferromatic pattern, the ferroelectric pattern with a nice resolution below the diffraction limit. So this is where we got into this world, and then we acquire a neaSNOM microscope, sorry. But the thing is, in this case, the amount of photo you will collect with second harmonic generation, if we are lucky, is going to be in the range of 10,000 of counts to hundreds of thousands of counts per second. So we could not use a standard photodiode, so we had to have this single photon counter that we bought from Hamamatsu. And so this is basically the path. Sorry, maybe I should say a bit more. So we have an oscillators, so femtosecond oscillators from Coherent, actually, which delivers pulses of 38 femtoseconds, 70 megahertz, and 1070 nanometers, which enter into the microscope. Then we collect the scattered light, and then we go through a direct beam splitter. So here we have a standard photodiode for the linear optics, and we have also added a small camera to have some kind of idea of the shape of it. And then we go through a bunch of filters, because we have plenty of light here, and then we have only a few photons there. And then, as I was mentioning, we have this single photon counter. But these single photon counters deliver some TTL output, basically, and then we had to go through the single photon counter to the frequency counter and then to the neaSNOM electronics. So we cannot really use this lock-in detection, but you will see in a minute. And for a little bit of techniques also, it's typically here we have a very small active area of 50 microns, because we want a small dark current, which is in this case around 7 count per second, not too bad. So this is where I jumped into our first steps of near-field optics, so be gentle. Huh? So this is a typical image of our samples. It's 100 nanometer thick, so topography. So I should have maybe rescaled it, but here it's typically 6 nanometers, so it's rather smooth for 100 nanometers. And of course, in linear optical image, so we just plug the photon, so we don't see much. Mostly, I guess, topography related optics, but we have a little bit of it. It helps us to align on the tip, etc. So first, we might dig into this as well, but first it was not what we're interested. And then we unplug the photo detector. We plug the single photon counter to the microscope, and then we of course acquire only the DC, the O0, because then it's only a few counts per second. And this is the image we have. I'm done in 1 minute. But obviously, so we have some kind of contrast. We're happy everything is working together. But obviously, it does not look like this. It's about the same image. And if we look a bigger scale, then we clearly see that it looks more like certainly some kind of artifact of, let's say, interference with far field. So I will absolutely not risk any conclusion on this slide. Actually, maybe in 2 years, but not now. And but at that stage, we are kind of happy because all the setup is working together. So we have put all the parts. So now we can nicely dig into this science. So to be on time, I just jump on my conclusion. So typically, we are interested in these antiferromatic materials. There are Terahertz excitations, so we do near-field measurements and time resolve. Non-linear optics, time resolve non-linear optics, and obviously now we are really into this near-field harmonic imaging, and hopefully in a few months or years, I will be able not to put a drawing here, but a real image of our structures. And with this, I thank you for your attention.